All right, so now that we know the properties of the normal curve, we have to start thinking about what happens if you start messing around with the mean and the standard deviation for that normal curve. So I have two curves drawn here, and the question is, what's the mean and standard deviation for each of them? We can see the center is where the mean is. So on this one, the pink one, it's 0. And then over here on the blue one, it's 3. Okay, so that's where the center is. Now the standard deviation is 1 because you can see 1 is where the inflection point happens, and that's 1 away from 0. And then over here, it's 4. Oh, and 4, excuse me, standard deviation is not 4. The inflection point's at 4, and 4 is 1 away from 3, so therefore the standard deviation is 1 there as well. Now what does that imply for us? If two curves have different means, that means they have different centers. So the lower the mean would be more on the left, and then the higher mean would mean that the graph is centered more on the right. Okay? Now what else does that mean for us? The standard deviations, if they're the same, standard deviation is a measure of spread, right? So the larger the standard deviation, the more spread out it is, but if they're identical like this, that means they have the same spread outedness. It's a word, spread outedness. So therefore, they have the same shape, right? Standard deviation is going to kind of tell you your curvy shape. And since they're the same here, that's why the curves are identical shaped. They just have different centers because they have different means. All right, now what about the second setup? Now you can see, hopefully, that they have the same center here, that the middle for both of these curves is at 0. So that's why the mu is equal to 0 for both of them. Now the standard deviation is different. The standard deviation for the pink curve is 1 because that's where the inflection point happens. You can see right down there, halfway between 0 and 2 is where it hits, so it's 1. Now the blue curve, it's 2 because that's where the inflection point is for there. So the moral of the story is that if they have the same mean, they're going to have the same center for the curve. But different standard deviations mean you have different shapes to the curve. The larger your standard deviation, the larger your spread. And the smaller your standard deviation, the smaller your spread. So the pink curve is less spread out because it has a lot smaller standard deviation, right? They go hand in hand. And the blue curve is more spread out because it's got a bigger standard deviation. Now, I want you to notice a couple other things real quick. The pink curves, which I know they might not be pink on your paper if you printed black and white, but you can use a pink highlighter or whatever. These two curves, the pink ones for me, they are identical. No, I'm not kidding. They're identical. They're the same curve. I know they look really different, but see how the mean is 0 and the standard deviation is 1 for both of them. That means they are the same curve. Interesting. All right. They look different because you have played with the scale. I've altered the scale between the two pictures. And that means you've got to pay close attention to your scale, as always, because we learned that way back in chapter 2, that you can fiddle with how something looks just by playing around with the vertical scale. And that's exactly what was done here. The vertical scale is different for both of these. You can't see the scale. I didn't give you a y-axis with tick marks, but there's one there. And I've played around with it, and that's why they look different. If you wanted to think about it, the blue curve down below would be coming in low and then never reaching quite as high as the pink one and then coming back out, right? All right, also notice that the pink curve, it has a mean of 0 and a standard deviation of 1. That's really a nice curve. It's really special. It's the most special normal curve. It's called the standard normal curve because mean of 0, standard deviation 1 is really nice to work with and has historically been very nice to work with when they didn't used to have calculators and computers to do stuff. So the standard normal distribution, the standard normal curve, that's what the pink one is. It's got a mean of 0 and a standard deviation of 1. Matter of fact, I'll even put that in here. Cool. All right. Now, we have one other thing to talk about. We have two other things. Now that we know how the normal curve works, we've got to think about what area underneath it means. We learned that area under the uniform curve was probability, right? Call it uniform curve. It's really the uniform box, but hey, this area we found right back here, that's a probability. So we want to be able to do that same thing for a normal curve. So the question is, when we find that area, what's it going to mean and how do we find that area? Well, I'm going to teach you what it means right now, and then finding the area, that's what we're going to cover in section 7 too. So you can think of the area under a normal curve as two different things. You can think of it as proportion or as a probability. They're kind of two sides of the same coin. It's just a question of how you choose to think about it. But they basically mean the same thing. So we're going to do this with an example, and hopefully that'll make it clear to you. So I've got giraffe weights. They're normally distributed. As to be honest with you, most mammals are. Most giraffes weigh between this values, less on the edges. There are less really big giraffes, less really small giraffes. That's just how it is. Tigers would be the same way. Bears, most bears are in the middle. Very few are really huge. Very few are really small, etc. Okay? Probably assuming adult giraffes, to be honest with you, but whatever. All right, so they've got a mean of 2,200 and a standard deviation of 200 pounds. So we're supposed to draw a normal curve, which I did, with the parameters labeled. So you can see the tick marks here. 2,200 is the mean. 2,400 is 200 away from that. So you add on 200, you get the next tick mark. That's where the standard deviation is. Then 2,600, and then 2,800, and so on. And then go backwards as well. All right, so then you've got your normal curve. You're going to shade your region that represents giraffes that weigh less than 2,100 pounds. So 2,100, because this is a number line down here, it's just not the number line you're used to. I mean, in algebra, you're so used to seeing like 0, 1, 2, 3, and so on. But for us, we've got the middle of our number line to be 2,200, and our tick marks are each with 200. That's our x-axis. So 2,100 is exactly between 2,000 and 2,200. So you put a tick mark or a line right there at 2,100, and you want less than, so we shade to the left. All right, now the question is, what is this? All right, notice, by the way, how Minitab just magically tells us that it's 0.3085, and I wrote that right here. Now, how we get that, that's the next section. But for right now, how do we interpret it? Now, we can think of this two ways. You can think, okay, 30.85% of all giraffes weigh less than 2,100 pounds. That means the proportion of all giraffes. So if you think of all giraffes on the planet, 30.85% of them weigh less than 2,100 pounds. You can also think of it as a random chance. You can say, okay, the chances of me randomly selecting a single giraffe that weighs in that region, weighs less than 2,100 pounds, is 0.3085. So you can think of it as one giraffe selected out of many. Or you can think of it as proportion of all giraffes. Now, on the same token, and I made it go away for a second, but I'll bring it back, that also means, oops, that is not what I meant to do at all. Oh, there we go. Ta-da. You could also think of it as if 30.85% are less than 2,100 pounds, then 69.15% are more than 2,100 pounds. But wait, what about equals 2,100 pounds? What about that line right there? 2,100 exactly. So I talk about less than, I talk about more than, but equal to, remember, is 0. So the chance of you being exactly, or this giraffe being exactly 2,100.0000000 forever O's pounds is 0, because you just need a finer scale. You put a giraffe on the scale, it's 2,100.2 pounds, 2,100.23 pounds, and so on. If you have a finer scale, you could get more decimal places. That's because weight is a measurement, which means it's a continuous variable. There are always more decimal places to get if you could just go out and get them, right? If you just had a fine-tuned enough measurement. So the chance of being exactly 2,100 is the area of that line right there. But lines don't have any area. Lines are one-dimensional. They don't have a two-dimensional area. So the area of that line is 0. As always, continuous distributions. Now, not for discrete distributions, not for things like binomial. That you can do exact. But for continuous distributions, you cannot do exact probabilities. They are always equal to 0. Okay, we're done with section 7.1. We will see you back here for 7.2. That's where we're going to learn how to find that area 0.3085. And also we're going to learn how to say, if I gave you the 0.3085 to begin with, could you find me the 2,100? And the answer is yes, you can. You find both of those things with Excel or StatCrunch, or in our case, both of them, because we'll learn both. See you then. Bye.